Dear students, welcome back to Microcontroller and Embedded Systems. Now, next question we are going to study is explain ARM core data flow model with a neat diagram. ARM core data flow model, or the same question can be asked like von Neumann implementation of ARM. Von Neumann implementation of ARM. This is a diagram very neatly you have to write. Here the main thing, first thing I want to explain you about buses. What is a data bus? Bus takes people from one place to another place. Same way here buses concept used to take data from one place to another place. So it's called data buses. Where buses two types, data bus and address bus. Which is used to carry data then called data bus, which is used to carry address called address bus. Here data bus. Okay, now programmer can think of an ARM core as a functional unit connected by data buses, connected by all the functional units connected by data buses. As shown in the figure, arrow represents the flow of data. The lines represent, this all lines represent buses, and the box represent operational unit or storage area. Data enters the process through data bus. Data may be an instruction to execute, or data may be what I call data item, simple data item. Von Neumann implementation, we call it as von Neumann implementations. Data items and instructions share the same buses. Harvard implementation of two different buses they are using in Harvard implementation. Now we study this. Each instructions executed belongs to particular instruction set. ARM processors, what we call, they are uses load and store architecture. Okay, first, okay, remember this. Yeah, if you first writing diagram itself carries a full marks. Okay, the main thing is that, okay, remember instruction decoder here. Instruction decoder translates the instructions before they are executed. Each instruction executed belongs to particular instruction sets. Next one, okay, next very important thing you have to remember is your instructions about ARM processors uses load and store architecture. Load instruction copies data from memory to register, load, where store copies data from register to memory. Okay, now, you can see this two source registers are there here. R0 to R15 register files. We are going to study next question registers. Then here Rn and Rn, that I call it as a two source registers. Okay, then RD is destination register. Okay, everything will be operated by registers only. Next concept ALU, arithmetic logic unit, or MAC nothing but multiply accumulate unit. Okay, it will take the values Rn and Rm from A and B buses and computes the results. Okay, data processing instructions write result in RD, this RD. Okay, remember that directly to register files. Suppose I am taking move R0 comma 10. I am writing 10 is moved to R0 register. Then move R1 comma 15. 15 is moved to R1 register. Now add addition. It will go to ALU, addition will be done and stored back to the register where you mention. So this is the structure it's working. Some shifting operation is the barrel shifter is used. Same way multiply, accumulate, unit also, MAC is also used. Next, one important feature of RAM, what I call the main thing is, one important feature of the ARM is that register RM alternatively can be pre-processed in the barrel shifter before it enters to ALU. It can enter to barrel shifter before it goes to ALU. Together, barrel shifter and ALU can calculate a wide range of expressions and addresses. Next, after passing through the functional units, the result RD is written back to the register file, result bus. I call it as a result bus. You can see here, result bus. For load and store instructions, incrementer incrementer is here. Okay, here always remember load and to store, two instructions available, very important. Okay, always you remember load means load instruction copies data from memory to register, where store means store copies data from register to memory. Okay, now, yeah, next very important things, incrementer. This load and store instructions, the incrementer updates the address register before the core reads or writes next register value from or to the next sequential memory location. Processor continues executing instruction until exception interrupts changes. Okay, executions flow. Okay, if you write this diagram, you'll get full marks. You have to write this diagram. That's a very important thing. And explain one word about each thing. What is data? What is data bus? What is the instruction decoder? Okay, what is the R0 to R15 registers? Okay, simple. Okay, very easy concept. Next question is, wait, we'll see the next important question. What is the next important question? Yeah, question set I have given to you. Okay, explain the, okay, briefly ARM processor based embedded system software. Embedded system software. Okay, what it contains. First diagram you have to draw. Diagram you have to draw neatly. That is the main very important thing. And keywords your this is an embedded system needs a software to drive it. This is the following picture. Shows that about the softwares. Okay, what it does. Okay, following figure shows the, yeah, typical software components required to control embedded devices. Embedded system software. Question is embedded system software. You have to draw the diagram. Applications, operating systems, initializations, device drivers, and hardware. These things. First one is initialization code. Okay. First one is applications. This application is the one of the tasks required for device. Particular applications. Embedded systems. What we do? Embedded system is designed for special tasks or specific tasks. Particular application purpose. Example: mobile phone might have diary application like this. Particular applications. Next is operating systems, provides infrastructure to control applications and manage hardware system resources. Next is initialization. First code executed on the board. First code executed on a board and is specific to a particular target or group of targets. Set of minimum parts of the board. Set of minimum part of the, yeah, set of minimum parts of the board before handing control over to the operating system. It's called initialization code. Next is hardware devices or device drivers. Device drivers provide a constant software interfaces to the peripherals on the hardware device. Now we will study this part, initialization part. Initialization part, yeah, thing contains three important things. First one is initialization code. Take the processor from the reset state to a state where the operating system can run. So it's called initialization, boot. Usually configures the memory controller and processor caches, initializes some devices. Initialization code handles a number of administrative tasks prior to handling control. What are the tasks? Three important phases are available that should be highlighted. First one is initial hardware configuration. What is this initial hardware configuration? Involves the setting up the target platform so that it can boot an image. The target platform comes up in a standard configuration, but this configuration normally requires modification to satisfy the requirement of the booted image. Example, memory system normally requires a reorganizations of the memory map. Initialization or organizing memory is an important part of the initialization code because many operating systems expect a known memory layout before they can start. Memory mapping, remapping. Memory remapping allows the system to start the initialization code from ROM at power up. ROM at power up. The initialization code then redefines or remaps the memory map to place RAM at address 000. to an important step, because then if the exceptions vector variable can be in RAM, thus can be reprogrammed. So it can be reprogrammed. Second point is here diagnostic. Diagnostic often embedded in the initialization code. Diagnostic code tests the system by exercising the hardware target. Check if the target is in working order. It also tracks the standard systems related issue. Okay. Primary purpose of diagnostic code is fault identification and isolation. Next is booting. Booting involves loading an image and handing over to that image. Boot processes itself can be complicated if the system must boot different operating systems, different versions of the same operating systems. Booting an image is the final phase, but first you must load the image. Loading an image involves anything from copying an entire program, including coding data into the RAM, just copying a data area containing volatile variable into RAM. Okay, next operating systems. Operating systems, you know very well, not a problem. But here remember, yeah, here real-time operating systems, RTOs, or platform operating systems. Platform Unix is an example. Real-time operating system, embedded systems is an example. Okay, which is next question. Wait, yeah, next question is yeah, registers. Correct. Registers available.